Our problem this time has a sphere of metal in which a circular cylinder is cut out, and the sphere's got a radius of 4, so there's our cross section that's given to us. Our radius is 4 there, so when we look at our cylinder that's been in there, we've got a radius of the cylinder and our radius and the height of the cylinder there. We want to find the volume of the cylinder here in terms of h. So to do that, we really need r in terms of h, because we need our relationship between r and h to be given. Now, if we look at that, this is where some problem solving starts to come in, because we've got to get, how do we get r in terms of h? Well, notice the triangle we've drawn here that would have a hypotenuse of this right angle triangle that we can cut out and look at, and the other sides of hypotenuse of 4, radius of the one side of the radius and the other side half h. Hopefully you can see that from that diagram. So from that we can apply Pythagoras' theorem, because 4 squared is equal to r squared plus a half h all squared. So we get h squared as half h all squared as h squared on 4. And then we can write r in terms of h. So, and notice I'm going to leave it just as r squared. I don't need to do too much more with it, because I've kept in mind the idea that my volume of my cylinder would be pi r squared times h. So I don't really need to square root it and then square it again. That's just doing too much work. So r squared is equal to 16 minus h squared on 4, which is equal to h. And now it's just about the manipulation of algebra to get down to what we want, because we multiply, we can take our h out the front that way, we get pi h, and then we can factorise a quarter out of that one to get a quarter pi h, 64 minus h squared. So once we've got our area, our volume, and subbed in r squared, and so the whole function's now in terms of h, it was just about manipulating the algebra and doing that. Then we want to find the maximum, find the value of h, so the volume of a cylinder is a maximum. Well, that's what the whole crux of the problem is, but we needed that volume in terms of h to start off with. Now notice I've just multiplied through by the h, because the quarter of pi is just a constant, so I keep my constant out the front. And instead of doing the product rule, I've just multiplied through by h to give us a function where I can just differentiate what's inside the bracket. So 64h becomes 64, and 3h cubed becomes 3h squared. Now, if that's going to be set equal to 0, the quarter pi doesn't really make much difference to when it's set equal to 0. So really only what's inside the bracket can be equal to 0. So that means that's where the quarter pi goes. If you're wondering what happened to it, I'm just ignoring it because only the bracket can be equal to 0. So I've set the bracket equal to 0 and start manipulating to get 3h squared is 64. And h squared would equal 64 on 3. So h would equal 8 on root 3. Technically, plus or minus 8 on root 3. But seeing we're dealing with a height, I ignore them. Minus 8 on root 3. A second derivative would be, well again, just keep the quarter pi out the front, derive what's inside the bracket, the 64 goes, gives us minus 6h. So I found the value of h that should make it a maximum or minimum. When h is equal to pi on 3, I sub that in, I get my second derivative less than 0. So it must be a maximum. So because I'm putting a positive number in, minus 6 makes the whole thing negative. So a maximum volume exists because of that fact. So there's my value of h. Proved that it was a maximum. And so I've solved my problem. This time we've got a wire, which is 30 centimeters in length. So I've just done a little diagrammatic representation there. 30 centimeters in length, and it's cut into 2 pieces. And one piece is used to make an equilateral triangle, the other's to form a circle. And we're told to take the wire to use to form the triangle as 3x. So that's the 3x there, comes out and makes that one. What's left over is 30 minus 3x. So that makes up the circumference of the circle. Now, we have a look here. We need to find the sum of the areas, all in terms of x. Well, that's not an easy thing to do at times. If we've got an equilateral triangle there, then every side must be x, because it was 3x the pieces y was 3x there. So that made it easier to get the sides being x. Now, I've used Pythagoras' theorem. I've dropped a perpendicular down to make that being, and let that be h, so I can find my perpendicular height. And the base is x there. So we get h squared equals to the hypotenuse squared minus the other half of this, the base, which is the other side, all squared. And I'm able to manipulate to get h in terms of x root 3 on 2x. So remember, that's our first step of the problem. Because if we look at our area, and before we should have looked at the area of this one would be the half base times the height, and pi r squared. So we needed h in terms of x, and as well as r needs to be in terms of x as well. So that's what we're doing in this part, to be able to substitute and get our base and our height. So we had our base in terms of x, there's our height, so that's h, and we got the pi r squared. So we need to get r in terms of x as well to get a function in terms of x. Before we go on, we could have done this, because we know it's an equilateral triangle, we could have used trigonometry to find and not have to worry about h. So the area for this one would be half times x times sine of 60 would give us the root 3 on 4x squared. So just be wary of that. You could use trig to solve that one. The circumference here is the 30 minus the 3x. So the circumference of this circle is 2 times pi times r. So if we divide by the 2r here, that's going to give us a function for r in terms of x, which is what we need to substitute it in the area for pi r squared. So from this point down to here, what we need is all just getting a manipulation of algebra. The root 3 on 4x squared just goes all the way down. What we've done here, we've started to factorize first. So we factorized 3 and 2 pi out from this function here. So we've had a common denominator, so the 2 pi come out, the 3 come out, so that leaves us 10 minus x, which allows us just to square each part here. So the 3 squares gives us 9, 2 squares gives us 4, we got pi squared with the pi out the front, and 10 minus x all squared, and then our pi's cancel to give us the 9 on 4 pi. Remember, that's just a constant out the front. That's the same type of thing. It's just a constant out the front of these brackets to be able to do our next part, which is to find the length of y that must be used so we get a minimum area there. So sorry, to get the areas of two figures is a minimum. So we get our first derivative. The first one's pretty easy because the 2 just comes down, cancels with the 4. 9 on 4 pi for the second one. Again, we're just doing the chain rule. So 2 comes down, subtracts 1 from the power, and then multiplies by the derivative of the bracket, which is just minus 1. So, which is important we don't forget that, because it's a negative value. So it's going to change our signs. We expand all that out. We get, instead it equal to 0, because we want to prove it's a minimum. So we get the root 3 on 2x, 90 minus 2 pi, when we multiply the 9 on 4 pi by the 2 by 10 by minus 1. And the 9 on 4 pi times 2 times minus x times minus 1 gives us 9x on 2 pi. So we've just expanded that bracket. And now we're manipulating to get collected our x's. So these two, the x's come out there, and we get the root 3 on 2, 9 on 2 pi. And the 90 and 2 cancel to give us 45 pi, but we've taken it across the other side, so it becomes positive. And then we've got our function here, so I've just manipulated to get a common denominator of 2 pi, so we get root 3 pi on 9 over the 2 pi. And then we've just divided by all that on both sides, or multiplied by its reciprocal, to get x by itself. So that's where we get the 45 times the 2 pi gives us 90 pi, and the pi multiplies by that function up there, then root 3 pi plus 9, and then our pi's just cancel out there, and there's our value for x. Not a pretty value at all, and as you can see, it comes down to 18.7, approximately 18.7, but that's, we've got to get it exactly to start off with. Prove it's a minimum. We'll get our second derivative, which is not too hard a function, not too hard if we look at when we expand it out and we derive this function, we get root 3 on 2, the x would go. That's a constant, so it goes, and then 9 on 2 pi, because the x goes. So that leaves that whole function greater than 0, which must be a minimum because it's concave down. So it must give us the minimum. Sorry, concave up, which must give us the minimum. Sorry about that. So the piece of wire, approximately 18.7, which we proved there. We went through, made sure we got the minimum, proving the second derivative was greater than 0 for all values. So the curve was always concave up. So that's not an easy manipulation, not an easy manipulation to start off with to get our two expressions, but then get into the area, and then the algebra and the manipulation we need to take care with. So just if you're not sure, go back over it. We must be able to do all that manipulation of algebra. Okay, that's a necessary part of the problem to get it down and solve that equation. So make sure you can work out every line and see what happens with the algebra, the fractions, and all the work that's needed to get our values.